Hello. Tonight, we drift into the quiet wonder of the Milky Way galaxy, the vast river of starlight we call home. It is a place shaped by ancient suns, powerful forces, and hidden structures far larger than anything we can easily imagine. Our galaxy is not merely a scattered collection of stars. It is a living system, sculpted by billions of years of cosmic history and filled with mysteries waiting patiently to be discovered. Imagine yourself moving slowly through this immense expanse. Soft clouds of cosmic dust glow faintly as starlight passes through them. Invisible currents of energy flow between ancient objects, while colossal star clusters drift like islands in an endless sea of darkness. The Milky Way holds wonders formed over unimaginable stretches of time, each one quietly inviting curiosity and awe. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, all you need to do is relax. Let the day fade away. Allow your mind to loosen and settle as we begin this calm journey through the cosmos. Our galaxy is so vast that light itself needs about 100,000 years to cross it. Light feels impossibly fast to us. It races across a room in an instant, reaching your eyes before you are even aware it has moved. Yet when that same light attempts to travel across the Milky Way, it becomes almost slow by comparison. To journey from one edge of our galaxy to the other, it would take 100,000 years. The distance is so immense that it strains the imagination. The space between stars is not truly empty, but it is open enough for light to move freely, slipping past drifting atoms and tiny grains of dust. Because of this enormous scale, when we look deep into the Milky Way, we are not seeing it as it exists right now. We are seeing layers of history spread across vast distances. Light from faraway regions began its journey long before humanity ever appeared. Every faint shimmer in the night sky carries a trace of ancient time, reminding us that even the fastest thing in the universe becomes calm and patient when measured against the size of our cosmic home. At the very center of the Milky Way rests a supermassive black hole, with a gravitational grip strong enough to bend space itself. Hidden behind thick clouds of dust and stars, it cannot be seen directly, yet its presence shapes the entire galaxy. Stars near the core race along looping paths, revealing the invisible mass that governs their motion. From far away, its influence is subtle, but close to the center, it becomes overwhelming. Vast clouds of gas stretch and twist as they fall inward, heating up and glowing as they spiral toward the darkness. The black hole itself is silent, but the space around it hums with activity as matter rushes toward its grasp. This unseen heart anchors the Milky Way, guiding its rotation and helping to hold its stars together. Imagining something so powerful and yet so quiet, something capable of bending space without light or sound, awakens a deep sense of wonder. The core of our galaxy is not peaceful, but restless, ruled by an invisible giant. Long ago, the Milky Way consumed a galaxy nearly half its own size. In the distant past, a large companion drifted too close and was slowly torn apart by immense gravitational tides. Its stars, clusters, and streams of debris were pulled in and absorbed, becoming part of the galactic halo we observe today. Traces of this ancient merger remain visible as energetic stars and sweeping arcs of stellar material, marking the remains of the lost system. Astronomers can still identify these fragments by studying their motions and chemical signatures, which differ from those of stars formed within the Milky Way itself. This event likely thickened the galactic disk, stirred the dark matter halo, and influenced the formation of the spiral arms. It serves as a reminder that galaxies grow through acts of cosmic consumption, absorbing entire star systems over vast spans of time. The Milky Way we know today carries within it the remains of this vanished giant, a ghostly companion whose stars now shine as part of our own celestial home. Surrounding our galaxy is a quiet gathering of dozens of ancient satellite galaxies. Encircling the Milky Way, they form a subtle community of smaller companions. each moving through space in a slow, timeless dance around our luminous home. Each of these companions carries memories from a much earlier universe. They drift along long, graceful orbits, some so faint that they almost disappear into the surrounding darkness. Their stars are typically ancient and sparsely distributed, giving these galaxies a fragile, delicate appearance. Yet, despite their quiet presence, they play an important role in the Milky Way's evolution. As they pass slowly by, they tug gently at the galaxy's outer halo, stirring subtle waves that ripple through its vast dark matter envelope. Some have already begun to unravel, shedding thin streams of stars that leave pale trails wrapped around the Milky Way like ancient threads. By studying these companions, we learn how large galaxies grow, not through sudden, violent moments alone, but through countless soft interactions spread across unimaginable spans of time. They move like elders around a great family, each one preserving a chapter of cosmic history that deepens our understanding of how the Milky Way became the spiral we recognize today. The Sunday races through the Milky Way faster than a bullet. We often think of the Sunday as steady and unmoving, a warm and familiar anchor in the sky. In reality, it is speeding through the galaxy at a velocity far beyond anything we experience on Earth, moving faster than a bullet and carrying the entire solar system with it. Every planet, every moon, and every drifting grain of dust is swept along in this vast motion. The Sunday follows a broad, curved path around the galactic center, guided by gravity and shaped by the combined mass of countless stars. Although we cannot sense this movement, it is constant. It shapes the distant future of our solar system and determines which regions of the Milky Way we pass through over time. As the Sunday continues its journey, it moves through clouds of gas, faint fields of radiation, and shifting gravitational currents that subtly influence the space around us. This silent voyage has lasted for billions of years and will continue for billions more. The idea that our familiar star is, in truth, a traveler on an immense galactic path invites a quiet sense of awe. We are passengers on a journey that never truly pauses. Stars are born in clouds so cold that fire cannot exist within them. When people imagine the birth of stars, they often picture intense heat, roaring flames, and blazing light. The reality is far more unexpected. Stars begin their lives inside clouds that are colder than anything found on Earth, so cold that fire is impossible. These clouds are made of dust and gas drifting through the Milky Way, appearing dark because they block the light of distant stars. Within them, temperatures fall so low that molecules move slowly and gently. Here, gravity takes on the role that fire cannot. It draws the cold material inward, gathering it into dense pockets. As these regions grow more massive, they collapse further and pressure slowly builds. Over long spans of time, the center begins to warm. Only when the temperature rises to extraordinary levels does nuclear fusion finally ignite. In that moment, a silent, frozen cloud is transformed into a shining star. The thought that brilliant suns emerge from cold, shadowed knots of dust feels like a quiet cosmic secret. It reminds us that creation often begins in stillness, and that before any light appears, the galaxy forms its stars in places where warmth is only a distant promise. Our solar system drifts inside a vast bubble carved by ancient stellar explosions. We live within a large cavity in space, largely unaware of its presence. Long before humans appeared, massive stars near our region of the galaxy lived brief, intense lives and ended in tremendous explosions. These supernovas pushed vast amounts of gas outward, clearing a wide region around them. The result is a giant bubble that now surrounds our solar system. This space is filled with thin, hot gas, created by the shock waves of those ancient blasts, far less dense than the material found elsewhere in the Milky Way. Our Sunday and its planets move gently through this airy region, as if traveling through a quiet room left behind after a violent event. The edges of the bubble form walls of cooler gas, where the energy of the explosions finally faded. Astronomers can trace this structure by mapping the faint light emitted by the gas within it, realizing that our entire solar system resides inside the remains of long-vanished stellar giants offers a soft, humbling perspective. We are surrounded by the quiet echoes of ancient cosmic events that shape the space we now call home. The Milky Way is slowly consuming smaller galaxies. From a distance, galaxies may appear calm and unchanging, but they are dynamic systems that interact, collide, and merge over immense stretches of time. The Milky Way is no exception. It is gradually drawing in several smaller galaxies that circle nearby, continuing a process of growth that has been unfolding for billions of years. Their stars are drawn out into long, delicate streams that wrap around the Milky Way like thin ribbons. These streams trace the paths of smaller galaxies as they are slowly pulled apart. Gravity captures them piece by piece until their stars are fully absorbed and become part of the Milky Way itself. This process has occurred many times in the past and will continue far into the future. It helps explain why old star clusters and unusual stellar populations are scattered throughout the galaxy. The Milky Way grows through these ancient mergers, quietly incorporating the remains of smaller companions. Even now, faint systems such as the Sagittarius dwarf galaxy are being stretched and dismantled as they fall inward. The idea that our galaxy has been shaped by a long history of gentle yet relentless cannibalism is both unsettling and fascinating. It reminds us that even structures as immense as galaxies are guided by the patient pull of gravity. Some stars in the Milky Way are more than twice as old as Earth. The galaxy contains stars that formed long before our planet ever existed, with some dating back to a time when the Milky Way itself was still young. These ancient suns offer a rare glimpse into the early stages of the universe. Their chemical makeup reveals conditions from an era shortly after the first generations of stars were born and died. Because heavy elements had not yet been widely created by supernovas, these stars contain fewer of them. Their light is subtly different, their atmospheres simpler, and their histories far longer. Many of these ancient stars inhabit the galactic halo, a sparse region that surrounds the Milky Way, moving along paths that carry them far above the spiral arms. By observing them, astronomers can study the early universe in a quiet, direct way. These old suns have burned steadily for billions of years, preserving secrets from a time when the galaxy was just beginning to take shape. Their presence adds a deep sense of continuity, reminding us that long before Earth formed, the Milky Way was already glowing with starlight. The galaxy glows with light from stars too faint for any telescope to resolve. When we gaze at the Milky Way on a clear night, we see a soft, luminous band stretching across the sky. Much of this glow comes from stars so dim that even powerful telescopes cannot distinguish them individually. These stars are small and faint, yet they exist in vast numbers. Together, their combined light forms a gentle background that fills the galactic disk. Dust and gas scatter this light, creating the hazy appearance that defines the Milky Way's glow. Though invisible on their own, these faint stars contribute significantly to the galaxy's mass and structure. Their collective gravity helps guide the motion of brighter stars. Some are old red dwarfs that burn slowly and quietly for trillions of years. Others are young stars just beginning their long lives. The idea that the Milky Way shines with the combined breath of countless unseen suns creates a soft sense of mystery. What we see is not the light of a few bright stars, but the quiet chorus of multitudes whispering across the sky. Rogue planets drift through the Milky Way without a sun. Not every planet is bound to a star. Some worlds wander freely through space, moving alone through the darkness. These rogue planets likely formed within solar systems before being ejected by powerful gravitational encounters. Without a nearby star to warm them, they travel through the galaxy in deep cold. Their surfaces may be frozen solid, yet some could conceal warm interiors powered by internal heat. The thought of planets roaming alone carries a haunting sense of quiet beauty. These worlds do not follow neat, predictable orbits, but instead trace long paths shaped only by the gravity of the galaxy itself. They may pass close to stars, drift through clusters, or vanish into the galactic halo. Though difficult to detect, their existence is supported by simulations and suggested by faint observations. There may be more of these wandering worlds than planets bound to stars. Imagining these silent travelers gliding through the Milky Way invites a calm sense of wonder. In the vast darkness between the stars, entire worlds move unseen, cold and solitary, carrying their own stories through the night. A halo of gas hotter than any flame on Earth surrounds our galaxy. Far beyond the Milky Way's spiral arms lies an immense envelope of extremely hot gas, extending high above and below the galactic disk. This gas reaches temperatures far exceeding those of any fire found on Earth, becoming so energized that it emits faint X-ray light. Although it is incredibly thin, the halo contains enough mass to influence the motion of stars and satellite galaxies. Astronomers believe this hot halo is a remnant from the early formation of the Milky Way, a lingering trace of the processes that shaped our galaxy in its earliest days, as well as the ongoing activity of supernovas that push material outward. This vast halo also serves as a reservoir of matter that may one day drift back into the galaxy, fueling future generations of stars. Invisible to ordinary sight, it surrounds everything we know. It reminds us that the Milky Way is not merely a flat disk of stars, but a layered and intricate structure with components extending far into space. This hot, quiet atmosphere envelops our galaxy like an immense and ancient cloud. Radio waves from the Milky Way reveal the lingering echoes of exploding stars. Throughout the galaxy, ancient stellar deaths leave behind signals that travel farther and last longer than the visible light from their shattered remains. These signals take the form of radio waves, gentle in nature, yet powerful in reach. When a star ends its life in a supernova, the explosion sends shock waves rippling through space. Those waves energize the surrounding gas, causing it to glow at radio frequencies that can cross vast distances without quickly fading. Long after the visible flash has disappeared, this radio glow continues to drift quietly through the galaxy. Using sensitive instruments, astronomers trace these faint echoes, mapping the shapes of old supernova remnants hidden within dusty regions. Each ripple carries information about the strength of the explosion, the structure of the expanding cloud, and the elements released into space. Through these waves, we uncover the hidden history of stellar deaths that enrich the Milky Way with heavy elements. They allow us to study events far older than humanity, reaching back to eras when entire regions of the galaxy looked very different. In this soft radio light, the Milky Way speaks of its past, whispering memories of stars that once burned brightly and ended in dramatic silence. A teaspoon of a neutron star would weigh more than a mountain. Neutron stars are among the densest objects in the universe, born when massive stars collapse under their own gravity. After a supernova, their matter becomes so tightly compressed that ordinary atoms can no longer exist. Protons and electrons merge into neutrons, forming a substance unlike anything found on Earth. If it were possible to collect just a teaspoon of this material, it would outweigh an entire mountain. This extreme density alters the behavior of light, magnetism, and gravity in remarkable ways. Neutron stars often spin at incredible speeds, sending narrow beams of radiation sweeping through space. They also generate magnetic fields far stronger than anything produced by human technology. Their surfaces are extraordinarily smooth, with gravity so intense that even the smallest irregularities cannot persist. Over millions of years, these strange remnants slowly cool, releasing the heat trapped within them. By studying neutron stars, scientists gain insight into the limits of matter and the conditions that exist in the most extreme environments. The idea that so much mass can be packed into such a tiny space inspires a profound sense of wonder. Neutron stars remind us that the universe contains states of matter far beyond everyday experience. The Milky Way contains star streams that stretch across the sky like ancient rivers. Scattered throughout the galaxy, long chains of stars move together along gentle, curving paths. These streams are the remains of smaller galaxies and star clusters that were once intact, but were gradually pulled apart by the Milky Way's gravity. As they unraveled, their stars spread out along their original orbits, forming sweeping trails that can span vast distances. Though faint, these streams serve as records of the galaxy's past interactions. By examining their shapes and motions, astronomers can reconstruct the histories of the systems that contributed them. Some streams arc high above the galactic disk, while others flow quietly within it. Together, they reveal how gravity sculpts the Milky Way over time, redistributing stars across enormous scales. These delicate ribbons also help scientists map the invisible dark matter halo surrounding the galaxy. The paths of the stars trace the underlying gravitational field, offering clues about how unseen mass shapes their motion. In a quiet way, star streams show that the Milky Way is always changing. They carry memories of ancient encounters stretched across the sky as gentle reminders of the galaxy's long and complex history. New stars ignite in our galaxy every single second. Throughout the Milky Way, star formation never truly ceases. Within cold, shadowed clouds scattered along the spiral arms, gravity continues its patient work, drawing gas together into dense regions. Over time, these pockets compress and heat up until conditions become intense enough for nuclear fusion to begin. In that moment, a new star is born, adding its light to the ongoing story of our galaxy. Although it may sound unbelievable, this process occurs so frequently across the vast disk of the Milky Way that new stars ignite every single second. Some are small red dwarfs that will burn slowly and quietly for trillions of years. Others are larger and brighter, destined to live fast, luminous lives before ending in powerful supernovas. The regions where star formation takes place are shaped by turbulence, magnetic fields, and the leftover material from earlier generations of stars. Light from newly formed suns gradually pushes away surrounding dust, revealing clusters that shine against the darker background. These young stars also reshape their surroundings by releasing energetic winds, carving and sculpting the very clouds that gave them birth. This continuous creation of stars is one of the processes that keeps the Milky Way alive and dynamic. It ensures that even as older stars fade, fresh sources of light are always emerging. Some stars spin so rapidly that they would fly apart without the force of gravity holding them together. Within the Milky Way are stars that rotate at astonishing speeds, with their equators racing along at hundreds of kilometers per second, far faster than the rotation of our Sunday. Without the immense pull of their own gravity, these stars would tear themselves apart. Their rapid spin causes them to bulge outward, forming flattened shapes rather than perfect spheres. This distortion changes the temperatures across their surfaces, making their poles hotter than their equators. Such extreme rotation can generate strong magnetic fields and alter how material flows around the star. In some cases, gas is flung outward, forming glowing disks or rings in the surrounding space. Their speed also affects how they evolve, influencing how they burn their fuel and how they will eventually die. By observing these rapid rotators, astronomers learn about the limits of stellar physics and how fast a star can spin before breaking apart. These stars reveal a more extreme side of the Milky Way, where gravity and motion exist in a delicate balance, showing that even stars experience tension between stability and the forces pushing them outward. Enormous cavities within the Milky Way contain vast regions of emptiness. Not every part of the galaxy is filled with stars and gas. Some areas are unexpectedly sparse, carved out by ancient events that swept material away. These enormous voids can stretch hundreds of light years across, leaving behind pockets of thin space within the spiral arms. Many were created by groups of massive stars whose intense winds and powerful supernovas pushed outward, clearing large volumes of the surrounding medium. Over millions of years, these explosions hollowed out bubbles that merged into even larger cavities. Though these regions contain far fewer particles than their surroundings, they are still shaped by the gentle pressure of nearby gas and the overall gravitational pull of the galaxy. Studying these voids helps astronomers understand how energy from dying stars reshapes the Milky Way. They reveal where stellar clusters once existed and how their activity influenced the surrounding environment. These vast pockets of emptiness stand in contrast to the dense molecular clouds where stars are born, reminding us that the galaxy is not uniform, but shaped by cycles of creation and destruction that leave behind both luminous birthplaces and quiet gaps in the stellar landscape. Diamond worlds may exist deep within our galaxy. Among the many strange planets scattered through the Milky Way are worlds thought to be so rich in carbon that their interiors could contain layers resembling diamond. These planets likely formed in regions where the building materials were very different from those near our own sun. Instead of being dominated by silicates and metals, they contain unusually high amounts of carbon, which becomes compressed under intense pressure. Deep inside these planets, that pressure may transform carbon into solid crystalline structures, similar to diamond. Their surfaces might appear dark and rocky, yet beneath them lies an interior shaped by exotic chemistry. Depending on how they formed, these worlds may orbit close to their stars or wander farther away. Studying such planets helps scientists understand the immense variety of conditions that exist across the galaxy. They demonstrate that planets can be profoundly different from those in our own solar system. Imagining entire worlds built from carbon-rich material with glittering layers hidden beneath their crusts inspires a quiet sense of wonder. These diamond worlds reveal that the Milky Way contains forms of planetary beauty far beyond anything we have yet seen on Earth. The Milky Way also contains stars capable of releasing bursts of energy powerful enough to scour nearby planets. Some stars in our galaxy are capable of unleashing sudden bursts of energy that far exceed the output of ordinary stellar activity. These powerful events occur when magnetic fields on a star's surface become twisted and stressed, then suddenly snap, releasing immense amounts of radiation. The energy involved can be so intense that it would strip atmospheres from nearby planets or dramatically alter their surfaces. Although such outbursts are rare, they reveal how unstable certain stars can be. The bursts race through space as brilliant flashes of light and streams of high-energy particles, detectable even from great distances by sensitive instruments. Studying these eruptions helps astronomers understand stellar magnetism and the environments surrounding these volatile stars. Many of them are young, still settling into stable patterns of rotation and energy release, while others are older stars with unusually strong magnetic fields. These sudden flares remind us that stars are not always calm, steady sources of light. They can be dynamic and unpredictable, sending powerful pulses that reshape the space around them. Some planetary systems contain dozens of worlds. While our own solar system has a relatively modest number of planets, the Milky Way hosts systems that are far more crowded. Certain stars are orbited by dozens of planets, each following its own distinct path. These systems form when large, dense disks of gas and dust collapse around young stars. Within these disks, material clumps together in many places at once, gradually growing into planets. Because the disks are expansive and rich in material, they can produce far more worlds than the system that formed Earth. These planets vary widely. Some are small, others massive, some icy, others rocky. Some orbit close to their stars, while others drift much farther out. Their interactions create complex gravitational patterns that evolve over long periods of time. By studying these densely populated systems, astronomers gain insight into how planets form under different conditions. They reveal just how diverse planetary architecture can be, even around a single star. The idea that some stars host vast families of planets expands our sense of abundance within the Milky Way, suggesting that the galaxy may contain endless varieties of worlds waiting to be discovered. Stars in the Milky Way can also be torn from their homes and sent wandering through space alone. Not every star remains where it was born. In some cases, powerful gravitational encounters fling stars out of their original systems. This can occur in crowded star clusters where close encounters are common, or when a star's companion explodes in a supernova, suddenly disrupting the balance of forces. Once expelled, these runaway stars travel through the galaxy on long, solitary journeys. They often move faster than most stars, slipping through the spiral arms and drifting into quieter regions of space. Though they may appear ordinary in brightness, their rapid motion reveals their dramatic pasts. Studying these wandering stars helps astronomers understand the dynamics of stellar systems and the forces capable of tearing them apart. These lone travelers offer glimpses into the more chaotic moments of the galaxy's history, showing that even stars can be uprooted and sent on paths that carry them far from their origins. In some regions of the Milky Way, stars are packed so tightly that they seem to blur together. These dense clusters form when large clouds of gas collapse, giving birth to hundreds or even thousands of stars at once. Because they form together, the stars remain close for long periods before slowly drifting apart. Within these young clusters, the distances between stars are far smaller than those separating stars near our Sunday. Their combined light merges into a brilliant glow that fills the surrounding space. Some clusters are nearly spherical, with stars crowded densely toward their centers, while others form looser groupings that still shine brightly through the dust of the galaxy. Studying these clusters provides valuable insight into stellar evolution, as the stars within them share similar ages, but differ in mass. Observations reveal how stars change as they grow, age, and eventually fade. Clusters also play an important role in shaping their environments. Powerful radiation and stellar winds from their stars carve cavities in surrounding gas, influencing where future stars will form. These crowded stellar communities remind us that many stars are born not in isolation, but in bright, bustling neighborhoods, glowing with shared light. Within the Milky Way, some molecular clouds are massive enough to give rise to thousands of suns. Across the Milky Way stretch enormous molecular clouds, vast structures composed mainly of hydrogen molecules, mixed with fine dust. These clouds are among the coldest and darkest regions of the galaxy. Yet, they hold extraordinary potential. A single cloud can contain enough raw material to create thousands of stars, similar in size to the Sun. Their immense mass allows gravity to gather the material into dense knots, where new stars begin to take shape. Over time, these regions collapse inward, igniting nuclear fusion deep within their cores. Despite their enormous scale, molecular clouds are surprisingly delicate. Radiation from nearby massive stars can slowly erode their surfaces, while shock waves from supernovas can compress them, triggering fresh rounds of star formation. Many of these clouds stretch for hundreds of light years, winding through the spiral arms like shadowed highways of future starlight. They are essential to the galaxy's ongoing life cycle, storing the ingredients needed to form new solar systems. Observing them requires specialized instruments, as they are opaque to visible light. Within these dark cradles, entire clusters of stars wait to be born, hidden from view until their growing light is strong enough to break through the surrounding gas. Some stars pulse in brightness like celestial heartbeats. Within the Milky Way are stars whose light brightens and dims in steady, rhythmic cycles. These pulsating stars expand and contract as changes in heat and pressure ripple through their interior layers. Each shift in size alters how much light they emit, creating patterns that can repeat over hours, days, or even months. These pulses act like stellar heartbeats, revealing information about a star's interior that cannot be observed directly. By measuring the timing and strength of the pulses, astronomers can determine a star's mass, age, and temperature. Some of the most well-known pulsating stars serve as cosmic distance markers because their brightness variations follow precise, predictable rules. They help map the structure of the Milky Way by providing reliable measurements of faraway regions. Pulsation can occur in young stars, aging giants, or stars passing through transitional stages of their lives, each with its own distinct rhythm. The gentle flicker of these stars adds a quiet sense of motion to the galaxy, reminding us that even points of light that appear steady can hide complex rhythms deep within their glowing layers. Shock waves from ancient supernovas still move through the galaxy. Long after the visible flash of a supernova has faded, the shock wave it created continues to expand outward. These waves travel through the Milky Way like ripples across a vast cosmic ocean, carrying the energy of the original explosion far into space. As they move, they compress gas clouds, heat interstellar material, and leave subtle changes behind. Some pass through dusty regions, shaping the material into intricate structures, while others move through emptier areas, slowly weakening, but still preserving the imprint of their violent beginnings. These shock waves can take tens of thousands of years to reach their full extent. Along the way, they may trigger new star formation by squeezing cold gas into dense regions. They also enrich the interstellar medium with heavy elements forged in the supernova. Modern telescopes detect these waves by observing the faint X-ray and radio emissions they produce, appearing as expanding shells or delicate filaments that trace the surrounding space. Even though the star that created them is long gone, its influence continues to travel quietly through the galaxy, shaping the environment for future generations of stars. Dust in the Milky Way was forged in the final breaths of dying stars. The dust that fills our galaxy has a dramatic and ancient origin. Much of it formed in the outer layers of aging stars as they neared the ends of their lives. When these stars expanded into red giants, their outer atmospheres cooled enough for tiny solid particles to condense. As the stars shed these outer layers, the particles escaped into space. Additional dust was created when massive stars ended their lives in supernovas, scattering newly formed elements into the interstellar medium. Over time, these dust grains spread throughout the Milky Way, becoming essential components in the formation of new stars and planets. They help cool collapsing gas clouds, protect fragile molecules from harsh radiation, and provide surfaces where complex chemical reactions can occur. Dust also absorbs and scatters starlight, giving the Milky Way its soft glow and shaping the appearance of nebulae. Each tiny grain carries the legacy of the star that created it. The realization that the dust throughout the galaxy, and even the material that eventually formed Earth, originated in the dying breaths of ancient stars, creates a gentle sense of connection to the vast cycles of cosmic life. A small number of stars orbit the galactic center at extraordinary speeds. Near the heart of the Milky Way, gravity becomes exceptionally intense. In this crowded region, a handful of stars move along their paths far faster than those found in the distant spiral arms. These remarkable motions were discovered through decades of precise measurements, tracking each star's position over time. Their tight, rapid orbits provide some of the strongest evidence for a supermassive black hole at the galaxy's core. As these stars swing close to the center, they trace sharply curved paths shaped by extreme gravitational forces. By studying their motion, astronomers can calculate the mass of the unseen object that governs their orbits. These stars also offer clues about the structure of the central region, which is filled with turbulent clouds of gas, powerful magnetic fields, and intense radiation. Despite the harsh environment, the stars themselves remain stable, shining steadily as they follow their dramatic routes. Observing them requires advanced infrared telescopes, capable of seeing through the thick dust that shrouds the galactic core. Their speed and precision provide rare insight into one of the most mysterious regions of the Milky Way, where space itself is warped by immense gravity. In some parts of the Milky Way, gravity subtly warps the path of starlight. As light travels through the galaxy, it may pass near regions rich in mass, such as dense star clusters, concentrations of dark matter, or heavy clouds of gas. When this happens, gravity bends the light's path, creating slight distortions. This effect can magnify, stretch, or shift the appearance of distant objects, a phenomenon known as gravitational lensing. Within the Milky Way, lensing allows astronomers to detect objects that would otherwise remain hidden, including free-floating planets and compact stellar remnants concealed in dark regions. It also helps scientists measure how mass is distributed throughout the galaxy, revealing the balance between ordinary matter and dark matter. The bending of starlight shows that the universe is not flat or simple. Even the light that reaches our eyes has been shaped by the gravitational landscape it passed through. This quiet distortion adds depth and complexity to our view of the sky, reminding us that every glimpse of the Milky Way carries subtle traces of unseen structures. Cosmic rays from our galaxy strike Earth every moment. Across the Milky Way, high-energy particles are constantly being accelerated by supernovas, energetic stars, and turbulent magnetic fields. These particles, known as cosmic rays, travel at nearly the speed of light and cross vast distances through space. Although Earth is shielded by its atmosphere and magnetic field, a steady stream of cosmic rays still reaches the planet at all times. Most are harmless, colliding with molecules high in the atmosphere and creating cascades of secondary particles that never reach the ground. By studying cosmic rays, scientists gain insight into the energetic processes taking place throughout the galaxy. Their energies reveal clues about the violent events that produce them, and their paths help map galactic magnetic fields as they curve through space. Though invisible, cosmic rays form a constant background of activity around our world. They remind us that Earth is not isolated, but connected to the dynamic and energetic workings of the Milky Way. Some stars are so hot that they can strip atmospheres from nearby planets. Certain stars in the Milky Way emit intense heat and ultraviolet radiation, gradually eroding the atmospheres of planets that orbit too close. These stars are often young or exceptionally massive, burning fiercely and releasing powerful winds of charged particles. When a planet is exposed to this relentless energy, its upper atmosphere heats up and begins to escape into space. Over long periods, much of the planet's air can be lost, leaving behind a dry, barren surface. This process plays a crucial role in shaping the evolution of planetary systems. Worlds that begin with thick atmospheres may slowly become airless, depending on their distance from their star and the star's intensity. Observing these interactions helps astronomers understand how stars influence the habitability of surrounding planets and how planetary atmospheres evolve under different stellar conditions. Their shapes reveal how the Milky Way grows by absorbing smaller galaxies. The paths of these stellar streams also trace the distribution of dark matter, bending in response to invisible structures that surround the galaxy. Tidal streams remind us that the Milky Way has lived a long and active life, shaped by repeated encounters with neighboring systems. Each interaction leaves behind a faint and beautiful signature. These drifting stellar remnants move silently through the night, carrying stories far older than Earth itself. Binary stars sometimes spiral together until they collide. In many regions of the Milky Way, stars are born in pairs rather than in isolation. These binary systems orbit one another in a gravitational dance that can continue for billions of years. Over time, some pairs slowly draw closer together. Their orbits shrink as they exchange energy through tidal forces, stellar winds, or interactions with surrounding material. Eventually, the stars may approach closely enough to merge. When this happens, the collision releases an enormous burst of light and energy, sometimes producing a brief but spectacular event known as a luminous red nova. The resulting star is often larger and brighter than either of the original pair, Such mergers help enrich the galaxy with heavy elements, as material is mixed and heated during the process. Studying these dramatic unions allows astronomers to better understand stellar evolution and the origins of certain rare objects. Though the process unfolds over immense spans of time, the idea of two stars slowly falling together until they become one adds a poetic sense of motion to the Milky Way. Even in the calm night sky, quiet celestial dances are always underway. Some worlds experience rain made of metal or glass. Among the countless planets scattered through the Milky Way are worlds with weather unlike anything on Earth. On certain intensely hot exoplanets, temperatures rise so high that metals evaporate into vapor. When the atmosphere cools slightly, these vapors condense and fall as shimmering metallic rain. On other planets, powerful winds carry molten droplets of silicate through the sky, creating storms of liquid glass that whip sideways at incredible speeds. The surfaces of these worlds may be covered by glowing oceans of lava, constantly reshaped by extreme heat. Such conditions occur on planets that orbit very close to their stars, or that formed with unusual chemical compositions. Their atmospheres reflect the intense radiation they receive, producing weather patterns driven by forces unfamiliar to us. Studying these exotic climates helps astronomers appreciate the vast range of environments planets can host. It shows that weather in the galaxy is not limited to water clouds and rain, but can include phenomena that feel truly otherworldly. Metal and glass rain transform distant planets into shimmering, dangerous landscapes shaped by heat and alien winds. Repeated supernovas have carved enormous cavities throughout the Milky Way. Across the galaxy, massive stars end their lives in powerful explosions that send shock waves racing into surrounding space. When many such explosions occur in the same region over millions of years, their combined energy can hollow out vast cavities. These regions contain far less gas and dust than their surroundings, appearing as enormous bubbles within the interstellar medium, sculpted by overlapping shock fronts. Inside these cavities, the gas is typically hot and thin, while their boundaries form denser walls where material has been swept aside. These structures preserve a record of star formation in their regions. Massive stars often form in groups, live brief lives, and explode within a relatively short period. Their collective activity reshapes the surrounding environment, influencing where new stars can later form. By studying these cavities, astronomers learn how energy moves through the galaxy. They reveal that the Milky Way is continually shaped by cycles of creation and destruction, each leaving behind vast hollowed regions as lasting imprints. Some stars exist in intergalactic space after being thrown out of their home galaxies. Not every star remains within the boundaries of the galaxy where it was born. Some are violently ejected during powerful gravitational encounters. When a star passes too close to a black hole or a tightly bound cluster, it can gain enough speed to escape the galaxy entirely. Once freed, it becomes a solitary traveler drifting through the vast emptiness between galaxies. These stars shine like any others, but their isolation makes them extremely difficult to detect. Their journeys carry them far from any familiar source of light or warmth, moving alone through the darkness of intergalactic space. The Milky Way has likely expelled many such stars over its long history. Some were thrown out during collisions with other galaxies, while others were cast away when a stellar companion exploded, suddenly disrupting the balance of forces that once held them in place. Studying these runaway intergalactic stars helps astronomers understand the extreme events that occur within galactic environments. They remind us that the universe is defined by motion and change, where even stars can be set adrift. These solitary wanderers move through the darkness, carrying with them the story of the violent moments that set them free. The Milky Way is home to ancient star clusters older than any planet. Scattered throughout the galaxy are globular clusters, dense, spherical gatherings of stars that formed when the Milky Way itself was still young. Many of these clusters are older than Earth older than the Sunday, and older than the planets of every known solar system. They contain some of the earliest generations of stars, formed before the galaxy settled into its familiar spiral shape. Within these clusters, stars move along tight orbits, packed so closely together that the sky would blaze with light if seen from inside. Their chemical composition reveals conditions from the early universe, long before heavy elements became widespread. These clusters orbit beyond the main disk of the Milky Way, drifting through the galactic halo on long looping paths. Observing them allows scientists to reconstruct the galaxy's early history and understand how its first structures took shape. Their great age lends them a quiet dignity. They have survived mergers, collisions, and countless cosmic upheavals, remaining as ancient survivors within a galaxy that has changed dramatically since they first ignited billions of years ago. Some stars in our galaxy rotate with blinding beams like cosmic lighthouses. These objects, known as pulsars, spin rapidly and emit narrow beams of radiation from their magnetic poles. As they rotate, the beams sweep through space, and when one points toward Earth, we detect a pulse of light that repeats with astonishing precision. The effect resembles a lighthouse turning in the night, though on a far more powerful scale. Pulsars are formed when massive stars collapse into neutron stars after supernovas. Their intense magnetic fields and rapid rotation make them among the most unusual stellar remnants. Some pulsars rotate several times per second, while others spin hundreds of times in that same interval. Their reliable pulses help astronomers measure distances, map regions of the galaxy, and test fundamental laws of physics. Pulsars also provide insight into how matter behaves under extreme compression. In systems where pulsars orbit one another, their motion can generate gravitational waves, ripples in space-time itself. These cosmic lighthouses add rhythm to the Milky Way, sending steady signals through the darkness that allow distant regions of the galaxy to be studied with remarkable clarity. Certain regions of the Milky Way glow with radiation left behind by past cataclysms. Throughout the galaxy are areas that emit faint yet persistent radiation, the lingering energy from ancient events such as supernovas, gamma ray bursts, or interactions between dense gas clouds and high-energy particles. The original sources of these disturbances may be long gone, but their radiation remains as a lasting signature. Much of this glow appears in wavelengths invisible to human eyes, including X-rays and gamma rays. By observing these regions, astronomers uncover the hidden history of the galaxy, identifying places where powerful events once reshaped the surrounding space. Some of this radiation comes from electrons spiraling through magnetic fields, while other emissions arise from gas heated to extreme temperatures. These glowing zones serve as reminders that the Milky Way has endured many energetic episodes. Even though the explosions themselves occurred long before humans existed, their echoes continue to travel through space. This quiet radiation tells stories of immense forces that once stirred the galaxy, leaving traces that persist for millions of years. At the galactic center, clouds of gas move with speeds that defy intuition. Near the heart of the Milky Way, gas clouds behave in ways that seem almost unreal. Orbiting close to the central black hole, where gravity is extraordinarily strong, these clouds race along at astonishing velocities. Some travel at hundreds of kilometers per second, tracing elongated, looping paths shaped by the uneven distribution of mass in the region. The environment here is dense with intense radiation, powerful magnetic fields, and tightly packed stars, creating one of the most extreme and dynamic regions in the entire galaxy. These conditions create intense turbulence, twisting and stretching the gas clouds into strange and complex shapes. Observing this region requires infrared and radio telescopes, as thick layers of dust block visible light. When scientists track the motion of the gas, they see it rushing, colliding, and flowing in spirals that reveal the hidden structure of the galactic core. These rapid movements also allow astronomers to estimate the mass of the central black hole by showing how strongly it pulls on its surroundings. The speed and energy of this environment stand in sharp contrast to the calm appearance of the night sky. Deep within the Milky Way, clouds of gas dance at unimaginable speeds, shaped by forces far more powerful than anything experienced near Earth. Some worlds orbit their stars in minutes rather than years. Not all planets follow the slow, graceful paths familiar from our own solar system. Within the Milky Way are worlds that circle their stars so closely that they complete an entire orbit in mere minutes. These ultra-short period planets cling tightly to their stars, becoming intensely heated on the side that always faces the light, while the far side remains comparatively cooler. Their orbits are governed by extreme gravity and fierce radiation that continually strip away their atmospheres. Many of these planets may have lost much of their original material, leaving behind dense, rocky cores. Because of their proximity, they travel at extraordinary speeds, sometimes tens of kilometers per second. Studying these extreme worlds helps scientists understand how planets evolve under intense conditions, revealing how orbits shrink over time and how planetary bodies adapt to relentless heat. Their rapid motion also produces unusual cycles of day and night. The idea of a year lasting only minutes challenges our sense of planetary motion and highlights the remarkable diversity of systems that exist throughout the galaxy. The Milky Way also contains planets made almost entirely of water. Among the many worlds scattered across the galaxy are planets believed to be dominated by water in forms unfamiliar on Earth. These worlds may hold vast quantities of water, ice mixed with high-pressure liquids that behave in exotic ways. Thick atmospheres could trap heat, creating layers of superheated water hidden deep beneath their clouds. Under extreme pressure, water can enter unusual states, forming dense crystalline structures. Such planets are often larger than Earth, with strong gravity capable of holding oceans hundreds of kilometers deep above rocky cores. Observing these worlds helps astronomers understand how planets form from different materials and under varying temperatures. Their existence expands our ideas about what a habitable world might be. Instead of continents and shallow seas, these planets could be covered entirely by global oceans, with no exposed land at all. Imagining entire worlds shaped by water, yet profoundly different from Earth, brings a quiet sense of wonder to our view of the Milky Way and reminds us how vast planetary diversity truly is. There are stars in the galaxy, so cool they could almost be mistaken for planets. Not every star in the Milky Way shines with intense heat. Some are so cool and faint that their temperatures barely exceed those of giant planets. These ultra-cool dwarfs emit most of their light in infrared wavelengths, making them nearly invisible to the unaided eye. Despite their small size, they are genuine stars, powered by steady nuclear fusion deep within their cores. Their low temperatures allow molecules to exist in their atmospheres, creating complex absorption patterns in their light. Studying these stars helps astronomers understand the lower limits of star formation and offers valuable clues about how planets might appear when observed from afar. Some of these cool stars host planetary systems where conditions may remain relatively gentle. Because they shine so softly, any life on nearby planets would experience a dim, reddish world. These quiet stars remind us that the Milky Way holds many forms of starlight, ranging from blazing giants to ember, like suns that blur the boundary between star and planet. The galaxy also contains enormous arcs of gas that stretch across vast distances. Woven through the Milky Way are immense arcs of gas, extending for light years at a time. These structures are shaped by a combination of stellar winds, supernova explosions, and magnetic forces that push and pull the gas over long periods. Some arcs form curved walls around ancient cavities, while others trace elongated paths carved by massive stars moving through the interstellar medium. Because this gas is often thin and cold, it can be difficult to detect, revealing itself only in wavelengths beyond visible light. Radio and infrared telescopes reveal the structure of these vast formations, tracing delicate curves that stretch across hundreds of trillions of kilometers. These sweeping arcs help astronomers piece together the history of star formation in their regions. Their shapes preserve evidence of past explosions, the flow of energy through the galaxy, and the ways in which clouds respond to gravity and pressure. They act like enormous cosmic brushstrokes, marking where powerful forces once moved through space. Seeing these graceful forms mapped across the Milky Way adds a sense of artistry to the galaxy, as if unseen hands shaped its gas into broad, elegant curves. Some star clusters drift together through space for immense spans of time. Throughout the Milky Way, groups of stars move in quiet harmony across vast distances. These drifting clusters form when stars are born together within the same cloud of gas. Over time, gentle gravitational interactions with other stars and interstellar clouds slowly pull the clusters apart. Even so, many of the stars continue traveling in roughly the same direction. These moving groups can persist for hundreds of millions of years, maintaining similar speeds and positions, even as they gradually spread out. Because the stars share a common origin, they tend to have similar ages and chemical compositions. Studying these groups allows astronomers to trace the history of star formation and understand how clusters dissolve over time. They also reveal how stars migrate through the galaxy, drifting far from their birthplaces into new regions. Some moving groups eventually disperse so completely that they blend into the general stellar population. Others remain coherent for long periods, like quiet caravans crossing the galactic landscape. Their gentle motion adds a sense of continuity to the Milky Way, showing how stars carry their shared beginnings with them as they drift. The Milky Way also contains stars that launch powerful jets of particles into space. Certain stars produce narrow, focused streams of matter that shoot outward at tremendous speeds. These jets often form when material spirals onto a dense object, such as a neutron star, or onto a young star still surrounded by a disk of gas. As the material falls inward, magnetic fields twist and channel it into slender beams that erupt into space. These jets can extend for vast distances, sometimes reaching light years from their source. Along the way, they illuminate surrounding gas, carving visible paths that reveal the structure of their environment. Around young stars, jets help clear away leftover material from the formation process. Around older, compact objects, the jets can become extraordinarily energetic, producing radiation detectable across the galaxy. These striking phenomena demonstrate how gravity and magnetic fields work together to create powerful and elegant structures. A star sending focused streams of energy into the darkness is a vivid reminder of how dynamic and creative the universe can be, where even relatively small systems can influence regions far beyond themselves. A small number of stars move so fast that they will one day escape the Milky Way entirely. Most stars follow stable orbits defined by the galaxy's overall mass, but a rare group travels at such extreme speeds that they are no longer bound to the galaxy. These hypervelocity stars are launched by intense gravitational encounters. Some are flung outward after passing too close to the central black hole, while others are released when a binary companion explodes in a supernova, suddenly breaking the gravitational bond. Once accelerated, these stars race outward on long trajectories, eventually drifting into intergalactic space. They shine like ordinary stars, yet their unusual velocities reveal the dramatic events that set them in motion. Studying these runaway stars helps astronomers understand the extreme conditions near the galactic center and the aftermath of supernova explosions. They remind us that even massive galaxies cannot retain all of their stars forever. Some will break free, carrying their light into the vast emptiness between galaxies. Their journeys will last billions of years, silent and solitary, shaped forever by the moment that sent them on their way. Some regions of the Milky Way are filled with clouds of energized plasma. Scattered throughout the galaxy are areas composed not of cold, neutral gas, but of plasma, matter in which atoms have been stripped of their electrons. These charged clouds respond strongly to magnetic fields, giving them behavior unlike that of ordinary gas. They can twist into long filaments, ripple like waves, or glow softly as electrons spiral through magnetic structures. Many of these plasma regions are created by massive stars or by supernova explosions that inject enormous amounts of energy into their surroundings, leaving behind glowing, dynamic clouds that trace the galaxy's energetic past. Others are shaped by turbulence within the interstellar medium itself. Studying these regions gives astronomers valuable insight into the Milky Way's magnetic environment, which cannot be observed directly. Plasma clouds act as tracers for the invisible magnetic fields that thread through the galaxy, revealing their structure and strength. They also influence how cosmic rays move, guiding or deflecting these high-energy particles as they travel through space. These charged regions add another layer of complexity to the Milky Way, showing that the space between stars is not empty, but filled with subtle energy, shaped by both matter and magnetic forces. Giant nebulae glow with colors created by energetic young stars. Across the Milky Way, vast clouds of gas shine brightly under the influence of newly formed, massive stars. These stars release intense ultraviolet radiation that energizes the surrounding gas, causing it to emit vivid colors. Hydrogen often glows with soft reds, while oxygen can produce gentle greens and blues. Many of these glowing nebulae are stellar nurseries. Within them, dense regions of gas collapse to form new stars, which eventually emerge from the clouds that created them. Stellar winds, radiation, and turbulence sculpt these nebulae into arches, pillars, and hollowed cavities, forming some of the most striking structures in the galaxy. Studying nebulae helps astronomers understand how stars are born and how they shape their surroundings. The colors themselves reveal the chemical makeup of the galaxy, as different elements shine in distinct ways when energized. These luminous clouds remind us that star formation is both a powerful physical process and a source of great beauty, filling the Milky Way with soft, colorful light. The galaxy also holds hidden brown dwarfs that never became full stars. Brown dwarfs occupy a quiet middle ground between planets and stars. They form when clouds of gas collapse in much the same way as star formation begins, but the resulting object never accumulates enough mass to ignite sustained nuclear fusion in its core. Without that energy source, brown dwarfs glow only faintly, radiating leftover heat from their formation. They can be far more massive than planets, yet remain too cool and dim to shine like true stars. Because their light is weak and mostly emitted in infrared wavelengths, many brown dwarfs remain unseen, drifting quietly through the Milky Way. Studying them helps astronomers understand the lower limits of star formation. Their atmospheres contain unusual molecules shaped by cool temperatures and high pressure, and some exhibit changing weather patterns that shift over hours or days. Although they do not burn like stars, brown dwarfs make up an important part of the galaxy's population, filling the space between bright suns with hidden complexity. Their faint glow and mysterious nature remind us that not all celestial objects fit neatly into familiar categories. Some worlds are covered in vast oceans of lava. Certain exoplanets orbit so close to their stars that their surfaces melt into glowing seas of molten rock. On these lava worlds, extreme heat prevents a solid crust from forming. Instead, rivers and oceans of liquid stone slowly flow under the pull of gravity and the influence of atmospheric winds. Temperatures on these planets can exceed the melting points of many minerals, turning their landscapes into brilliant, red and orange expanses. In some cases, strong tidal forces from nearby stars further heat the planet's interior, driving intense volcanic activity. Lava oceans are continually replenished as molten rock rises from below. Studying these extreme planets helps astronomers understand how worlds evolve under relentless radiation and heat. Their atmospheres may contain vaporized rock that condenses into mineral clouds, producing unusual forms of precipitation that fall back onto the molten surface. Lava worlds show that planetary environments in the Milky Way can be vastly different from anything on Earth, offering glimpses of landscapes forged under the harshest conditions imaginable. Pulsars in the Milky Way spin with the precision of cosmic clocks. Pulsars are rapidly rotating neutron stars that emit narrow beams of radiation from their magnetic poles. Each time one of these beams sweeps past Earth, it produces a pulse of light that arrives with astonishing regularity. Some pulsars are so stable that their timing rivals the accuracy of atomic clocks. This extraordinary precision makes them powerful tools for studying the galaxy, allowing astronomers to measure distances, probe gravitational effects, and explore the behavior of matter and space-time under extreme conditions. By observing subtle changes in pulse timing, astronomers can detect the influence of passing objects, gravitational waves, or internal changes within the pulsar itself. A pulsar's rotation is a direct remnant of the star that formed it. When a massive star collapses, its core shrinks dramatically, causing it to spin faster, much like a figure skater, accelerating when pulling their arms inward. Although pulsars gradually slow over millions of years, their early lives can involve hundreds of rotations every second. Powerful magnetic fields channel charged particles along narrow paths, creating the focused beams that make pulsars so distinctive. These objects act as natural laboratories for extreme physics, revealing how matter behaves under conditions far beyond anything achievable on Earth. The galactic center conceals vast reserves of molecular gas. Deep within the Milky Way's core lies an enormous concentration of cold, dense molecular material, rich in the ingredients required for star formation. Yet this region is anything but calm. Strong radiation, turbulent motion, and intense gravity constantly shape and disturb the gas. Clouds are stretched, compressed, and heated as they orbit close to the central black hole. Even so, some pockets remain shielded enough for molecules to survive. These protected regions host some of the most massive and active star-forming sites in the galaxy. Observing them requires radio and infrared wavelengths, capable of piercing the thick dust that obscures the core. The distribution of this molecular gas helps astronomers understand how stars can form under extreme conditions and how energy flows through the galactic center, influencing nearby regions. These hidden reservoirs play a vital role in creating new generations of stars, showing that even the harshest environments can support creation. There are rare systems where two planets orbit one another like dance partners. Not all planets circle stars alone. In uncommon cases, two planets of similar mass form close enough to share a mutual orbit. Rather than one dominating the other, they revolve around a shared center of gravity located between them. These double-planet systems move together through space like partners in a slow, graceful dance. Their shared motion affects their rotation, tidal forces, and long-term stability. Detecting such systems is difficult, as they can appear similar to single planets from a distance. Careful measurements, however, can reveal small variations in their motion that hint at their dual nature. These arrangements offer valuable insight into how planets form and interact, showing that worlds can develop in cooperative pairs rather than solitary paths. Their existence highlights the remarkable diversity of planetary systems within the Milky Way. Imagining two planets bound together in a cosmic waltz adds a quiet elegance to the galaxy's vast variety. Some stars are shaped into flattened spheres by extreme rotation. Certain stars spin so rapidly that their equators bulge outward under centrifugal force, while their poles remain more compact. This distortion affects how heat is distributed across the surface. The poles tend to be hotter and brighter, where material is more tightly compressed, while the equatorial regions appear cooler. This effect is known as gravity darkening. Rapidly rotating stars are often young and massive, retaining much of the angular momentum from their formation. Their spin also influences their evolution, allowing internal layers to mix more efficiently and altering how they consume fuel. Observing these stars helps astronomers understand the complex relationship between rotation, structure, and energy output. Their distorted forms challenge the simple image of stars as perfect spheres and reveal that even familiar points of light can hide unusual physical behavior. These flattened stars add yet another layer of diversity to the Milky Way, showing how motion alone can sculpt a star into an unexpected shape. Massive supernova remnants continue to glow with intense energy long after the explosion itself has faded. When a massive star dies in a supernova, it leaves behind an expanding cloud of gas and debris known as a remnant. These remnants grow outward for thousands of years, colliding with and shaping the surrounding interstellar medium, even long after the initial flash of light has disappeared. The remnants remain luminous. Powerful shock waves heat the gas to extreme temperatures, sustaining a persistent glow that marks the site of the star's violent end, producing X-rays as well as visible light. The tangled filaments and dense knots within a supernova remnant preserve details about the original star and the immense force of the explosion. Studying these structures allows astronomers to understand how heavy elements are spread throughout the Milky Way and how energy released by dying stars reshapes nearby space. Over time, the expanding cloud slows and cools, eventually dissolving into the surrounding interstellar medium. Yet while it remains active, a supernova remnant stands as a vivid reminder of the dramatic endings of massive stars. These glowing clouds show that the aftermath of a stellar explosion stays energetic and informative long after the initial flash has faded. Some planets skim so close to their stars that they glow red-hot. Within the Milky Way are worlds that orbit at such close distances that their surfaces reach extreme temperatures. These close-in planets are often large and gaseous, with atmospheres that swell and shimmer under relentless stellar radiation. The heat causes their clouds to glow, sometimes bathing the entire planet in a reddish or golden light. On their day sides, temperatures can become high enough to vaporize minerals and metals, producing exotic atmospheric chemistry. Powerful stellar winds continually strip particles from their upper layers, forming long tails of gas that stream behind them as they orbit. These worlds circle their stars rapidly, sometimes completing an orbit in only a few days. Studying them reveals how planets endure and evolve under such intense conditions. Their structure, weather, and atmospheric loss offer valuable insight into planetary survival in extreme environments. These glowing worlds remind us that the Milky Way contains planets far stranger and more varied than those in our own solar system. The Milky Way also contains clouds where ice crystals form in open space. In the coldest and most sheltered regions of the galaxy, far from harsh starlight, clouds of gas can cool enough for molecules to freeze onto tiny dust grains. These frozen layers form delicate ice crystals made of water, carbon dioxide, methane, and other compounds. Such ices play a crucial role in interstellar chemistry. They provide surfaces on which complex molecules can slowly assemble, building the raw materials that may later become part of planets or even life. Infrared observations reveal these icy coatings through their distinctive absorption signatures. Hidden behind thick veils of dust, these frozen clouds remain invisible to ordinary light. Studying them helps astronomers understand the earliest stages of star and planet formation, showing how quiet and cold the galaxy can become in its most protected corners. These icy environments act as gentle incubators, where chemistry unfolds patiently over millions of years. Ancient red giants enrich the galaxy with heavy elements. Red giants represent a late phase in the life of many stars. As they exhaust the hydrogen fuel in their cores, they expand and cool, becoming vast and luminous. Within their extended envelopes, nuclear reactions create new elements. Over time, red giants lose their outer layers, releasing this enriched material into space. The expelled gas and dust become part of the interstellar medium from which new stars and planets will form. In this way, red giants supply the Milky Way with essential building blocks for future generations of celestial bodies. Their slow, steady winds carry carbon, nitrogen, and other vital elements far across the galaxy. Observing red giants helps scientists trace the chemical evolution of the Milky Way. Their soft glow and continuous contribution to the cosmic cycle add a sense of continuity, reminding us that creation and renewal are woven into the life of every star, even those nearing the end of their luminous journey. Some stars wander along orbits that span vast portions of the galaxy. Not all stars follow smooth, circular paths around the Milky Way. Some move on elongated trajectories that carry them across immense distances, from one side of the galaxy to the other. Along these journeys, they pass through regions with dramatically different densities of gas, radiation, and gravitational influence. Many of these stretched orbits originate from stars that once belonged to smaller satellite galaxies, later absorbed by the Milky Way. As those galaxies were torn apart, their stars were captured and placed on wide-roaming paths. Other stars may have been pushed into eccentric orbits through close encounters with massive objects. Their routes can lift them far above the galactic plane before drawing them back through the spiral arms. Observing these travelers allows astronomers to study the Milky Way's structure and mass on the largest scales, revealing how gravity shapes motion across the galaxy. Their motions reveal how the Milky Way's gravitational field changes from one region to another. These wandering stars act as quiet messengers from the galaxy's past, carrying evidence of long-vanished mergers and ancient interactions. Their wide, looping paths show that the Milky Way is not a static disk, but a dynamic system shaped by countless events. Over time, the galactic halo is home to faint stars that drift like cosmic ghosts. Surrounding the bright disk of the Milky Way is a vast halo filled with extremely old and dim stars. They move slowly through space, far from the crowded regions where new stars are forming. Many of them were born in the earliest eras of the galaxy, before the spiral arms took shape. Their low brightness makes them difficult to observe, and their wide distribution leaves them separated by immense distances. These halo stars often have unusual chemical compositions, containing very small amounts of heavy elements. Studying them allows astronomers to glimpse conditions that existed shortly after the universe first began forming stars. Some belong to ancient clusters that have survived for billions of years, while others were once part of smaller galaxies, later absorbed by the Milky Way. Because the halo is so sparse, its stars appear isolated, shining quietly against the deep backdrop of space. They preserve the Milky Way's earliest chapters, still present even as the galaxy has changed dramatically around them. There are worlds locked in perpetual twilight between two suns. In certain binary star systems, a planet can settle into an orbit that keeps it balanced between both stars. In this arrangement, the combined light creates a world bathed in constant dusk. The sky would rarely grow fully dark, and true daylight might never arrive. Illumination would shift gently as the stars move along their own orbits. But darkness would remain uncommon. Temperatures on these worlds depend on their distance from the stars and the intensity of the light they receive. Some twilight planets may be mild, while others could be cold or warm enough to allow liquid water. The gravitational influence of two stars creates complex orbital patterns, yet many of these configurations can remain stable for long periods. Studying such systems reveals how planetary environments can differ in unexpected ways. showing that sunlight is not always singular or simple. These softly lit worlds offer a vision of planetary life shaped by a constant, gentle glow. Stellar nurseries within the Milky Way can give rise to entire star clusters at once. Deep within the galaxy are vast reservoirs of cold gas where new stars are born. Rather than forming in isolation, stars often emerge in groups. As gravity draws large clouds of gas inward, the material fragments into many dense regions. Each of these pockets can collapse to form a star, resulting in clusters that are born together. These groups may include stars of many different sizes, from massive blue giants to small red dwarfs. The stars interact through gravity and radiation, shaping their shared environment. Young, massive stars produce intense light and powerful winds that carve cavities in the surrounding gas. Depending on how the remaining material responds, these forces can trigger further star formation or bring it to an end. Once the gas is dispersed, the newly formed cluster begins to drift through the galaxy. Over time, some clusters remain bound, while others slowly dissolve and blend into the galactic background. Studying these nurseries shows how the Milky Way continually renews itself, building new generations of stars in waves of creation. Some stars shed their outer layers in vast, shimmering shells. As certain stars approach the end of their lives, internal changes cause them to release their outer atmospheres. This material expands outward, forming large, glowing shells of gas that surround the fading core. The gas shines softly because the remaining central star heats it from within. These graceful structures are known as planetary nebulae. Despite their name, they have nothing to do with planets. Each one displays a unique shape influenced by the star's rotation, magnetic fields, and the motion of nearby material. Some nebulae form rings, others take on butterfly-like shapes, and some appear nearly spherical. Over time, the gas disperses into space, enriching the interstellar medium with elements forged inside the star. These luminous shells represent a brief but striking phase in the life cycle of low to medium mass stars. They offer vital clues about how stars evolve and how they return newly forged material to the galaxy. Their fragile, intricate forms turn the quiet death of a star into a luminous event, one that continues to expand and influence its surroundings for thousands of years. The Milky Way contains unusual carbon stars that glow with deep crimson light. Among the galaxy's countless stars are some that shine with an especially rich red hue. These carbon stars possess atmospheres saturated with carbon-based molecules that absorb blue light, allowing deep red tones to dominate. They form when aging stars dredge carbon up from their interiors and mix it into their outer layers. This shift in chemistry dramatically alters the star's appearance. Carbon stars often shine brightly in infrared wavelengths, making them stand out in surveys of the Milky Way. They also produce significant amounts of dust, contributing fresh material to the interstellar medium. Studying these stars helps astronomers understand how elements are recycled through stellar evolution. Their warm red glow adds variety to the galaxy's stellar population, showing how subtle chemical changes can profoundly shape the light we see. Some worlds are tidally locked and never experience a sunrise. Many planets orbit their stars in a way that causes the same side to always face the light. These tidally locked worlds have a permanent day side and a permanent night side. On the illuminated side, temperatures can soar, while the dark side may remain locked in frozen darkness. Between them lies a narrow twilight region, where conditions can be far more moderate. Atmospheric circulation on these planets redistributes heat, creating wind patterns and cloud systems unlike anything on Earth. Some tidally locked planets orbit small, cool stars, where the habitable zone lies very close to the star itself. Despite their unusual lighting, such worlds may still be capable of supporting liquid water under the right circumstances. Studying them helps astronomers understand how climates function when sunlight never moves across the sky. Tidally locked planets reveal how flexible planetary environments can be, reminding us that familiar concepts of day and night take on very different meanings elsewhere in the Milky Way. Giant bubbles of radio emission rise above the galactic center. Extending far above and below the Milky Way's core are enormous structures that emit faint radio waves. These vast bubbles stretch for thousands of light years and are filled with highly energized particles. They likely form during periods of intense activity near the central black hole, or from powerful bursts of star formation that released enormous amounts of energy. Their smooth, rounded outlines suggest that strong forces pushed gas outward into massive lobes. Observing these bubbles allows astronomers to reconstruct the energetic history of the galaxy's core. Inside them, charged particles spiral along magnetic fields, producing the radio emission that outlines their shape. Their sheer scale is difficult to comprehend. Rising far beyond the galactic disk, they rank among the largest known structures in the Milky Way. Their presence reveals that the galaxy's center has experienced dramatic episodes whose effects still linger as a quiet radio glow. There are pairs of black holes hidden throughout the galaxy. Black holes are often not solitary objects, but members of binary systems formed when two massive stars evolve together. As each star reaches the end of its life, it collapses into a black hole. The resulting pair orbits a shared center of gravity, slowly spiraling inward as they lose energy through gravitational waves. These systems are extremely difficult to detect, since black holes emit no light of their own. Astronomers identify them by tracking the motion of nearby stars or by observing high-energy radiation when one black hole pulls material from a companion star. Some pairs remain quiet for vast spans of time, revealing themselves only through subtle gravitational effects. Binary black holes offer critical insight into stellar evolution, the deaths of massive stars, and the origins of gravitational wave events. Their silent motion adds a layer of mystery to the Milky Way as they drift unseen through space on paths that may eventually end in a violent merger, releasing immense energy across the universe. Some stars form surrounded by entire disks of dust that glow like embers. Young stars often emerge wrapped in broad disks of gas and dust left over from their formation. These disks glow with gentle warmth as starlight heats the tiny particles within them. The dust absorbs this energy and re-radiates it in infrared wavelengths, creating a soft, ember-like glow. Within these disks, planets are born. Over time, dust grains collide and stick together, forming larger clumps that grow into planetesimals, and eventually full-sized planets. The structure of these disks reveals the earliest stages of planetary formation. Rings, gaps, and spirals appear as emerging worlds carve paths through the dust. Observing these glowing disks helps astronomers understand how solar systems arise from simple clouds of material. They show that planets begin as microscopic grains, drifting within warm, swirling environments. These softly illuminated disks offer a glimpse into the very beginning of worlds, shining as delicate halos around the stars they surround. The Milky Way also contains worlds larger than Jupiter that drift alone through space. Scattered throughout the galaxy are enormous planets that no longer orbit any star. These rogue giants can exceed Jupiter in size and wander through the darkness in near silence. Most likely, they formed within young planetary systems, but were later ejected by violent gravitational interactions with other massive bodies. Once cast out, they continue on solitary journeys, warmed only by the faint heat left over from their formation. Some may retain thick atmospheres that trap internal warmth, while others could host slow-moving storms deep within their clouds. Detecting these planets is difficult because they do not reflect starlight. Instead, astronomers search for the faint infrared glow they emit or watch for subtle gravitational effects as they pass in front of distant stars. These lonely giants reveal how dynamic and chaotic planetary systems can be. Their existence suggests that planets are not always bound to the stars that created them, but may roam the galaxy indefinitely, far from any steady source of light or heat. They add a quiet, mysterious dimension to the Milky Way's population of worlds. There are stars that feed on their companions. In some binary systems, one star becomes dense enough to pull material from its partner. This occurs when a star evolves into a white dwarf, neutron star, or black hole. The compact object's intense gravity strips gas from the outer layers of the companion star. This stolen material forms a swirling disk around the feeding star, heating up as it spirals inward. The process can produce sudden bursts of radiation that appear as bright flares across the sky. Over long periods, the feeding star may gain substantial mass, altering its behavior and sometimes setting the stage for future explosive events. Meanwhile, the donor star can lose much of its outer envelope, changing its structure and shortening its life. These dramatic relationships reveal how closely bound stars can profoundly influence one another. They show that stellar evolution is not always a solitary journey. Some stars grow by consuming material from their neighbors, creating systems shaped by both cooperation and destruction. These feeding stars remind us that even distant suns can experience intense, transformative interactions. Some planets orbit dead stars. Though it may seem unlikely, planets can survive the violent transformation of a star into a stellar remnant. Some orbit white dwarfs, the hot, dense cores left behind after stars like the Sun shed their outer layers. Others circle neutron stars formed when massive stars collapse. These environments are extreme, often flooded with intense radiation. Yet certain planets endure. Some may have formed after the star's death, assembling from leftover debris, while others could have migrated inward over time. Around white dwarfs, planets can receive steady light and warmth once the remnant cools sufficiently. Around neutron stars, conditions are far harsher, with powerful magnetic fields shaping the planet's atmosphere. The existence of planets around dead stars challenges assumptions about planetary survival. It shows that worlds can persist, even arise, after dramatic cosmic endings. These systems offer insight into how planetary environments rebuild themselves and how resilient planetary formation can be. The Milky Way also contains regions rich in organic molecules. Spread throughout the galaxy are clouds filled with complex organic compounds. These molecules form on the surfaces of dust grains or within cold gas, where simple elements gradually combine into increasingly intricate structures. Some of these molecules are precursors to the chemistry found in living organisms, though their presence does not imply life itself. Instead, they demonstrate that the fundamental building blocks of biology can form naturally in many environments. These regions are typically found within dense molecular clouds, where temperatures are low and ultraviolet radiation is limited. Infrared and radio telescopes detect the distinctive signatures of these molecules, revealing how widespread they are. Their abundance suggests that chemistry in the galaxy is rich and diverse. Understanding how these compounds form helps astronomers learn about the earliest stages of planetary development. Over time, they may become incorporated into comets, asteroids, or even planets. The realization that organic complexity exists within quiet clouds, scattered throughout the Milky Way, creates a sense of connection to the broader universe. It shows that the seeds of chemistry are widespread, waiting patiently for the right conditions to unfold. Ancient supernova debris still drifts through the Milky Way. When massive stars explode, they hurl material far into space, carrying heavy elements forged deep within their cores. Over long periods, this debris spreads outward, forming filaments and clouds that move slowly through the interstellar medium. Some of this material mixes with molecular clouds, becoming part of future generations of stars and planets. Other fragments remain isolated, glowing faintly as they cool. Studying these remnants allows astronomers to understand the composition of supernovas and how elements circulate through the galaxy. These drifting clouds can be observed across many wavelengths, from radio waves to X-rays, depending on their temperature and structure. They stand as markers of the powerful events that shaped the Milky Way's chemical makeup. This debris forms a bridge between stellar generations, carrying the legacy of long-dead giants forward in time. Even after millions of years, these remnants continue to influence the galaxy's evolution. There are stellar bow shocks formed when stars plow through interstellar gas. As some stars move rapidly through the galaxy, they collide with clouds of gas in their path. This interaction creates a curved shock wave, similar to the bow wave produced by a boat cutting through water. The shock compresses and heats the gas, causing it to glow in infrared or visible light. The size and brightness of a bow shock depend on the star's speed, the strength of its stellar wind, and the density of the surrounding material. These structures provide valuable information about both the star and its environment. They show how stellar winds interact with the interstellar medium and how stars respond to the space they move through. Some bow shocks stretch across light years, forming graceful arcs that trace a star's motion. Observing them helps astronomers identify runaway stars and understand how high-speed interactions shape the galaxy. These luminous curves reveal that even stellar motion can leave visible marks on the surrounding gas. The Milky Way contains massive, hot stars that live fast and die young. Among the galaxy's stellar population are rare giants that burn their fuel at extraordinary rates. These massive stars shine with intense brightness and drive powerful stellar winds that sculpt their surroundings. Because they consume their hydrogen so quickly, their lifespans last only a few million years, a brief instant on cosmic timescales. Their ultraviolet radiation strongly affects nearby clouds, sometimes triggering new star formation and other times suppressing it. When these stars reach the ends of their lives, they explode as powerful supernovas, releasing heavy elements into the interstellar medium. Studying them helps astronomers understand how energy flows through the Milky Way. Their short but dramatic lives play a critical role in shaping surrounding regions. They carve nebulae, enrich the galaxy with new elements, and leave behind compact remnants such as neutron stars or black holes. These fast-burning giants show that not all stars follow slow, gentle paths. Some blaze brilliantly for a short time, leaving lasting imprints on the galaxy. Some worlds experience constant storms larger than Earth. Across the Milky Way are planets where massive weather systems never truly subside. These storms can span distances greater than the size of Earth and may persist for years, decades, or even centuries. Many of these planets are gas giants with deep atmospheres, driven by powerful winds and strong jet streams. Storms form where bands of atmospheric motion collide, creating swirling vortices that grow into immense, long-lived cyclones. Some storms appear as bright or dark spots that change in size and shape over time. Their colors reflect the chemical makeup of the clouds and the temperatures within the storm itself. Studying these immense weather systems helps astronomers understand how planetary atmospheres behave under different conditions. Their existence shows just how active and turbulent distant worlds can be. These powerful systems remind us that weather in the Milky Way is not limited to gentle winds or light rain. On some planets, storms reach scales and energies far beyond anything ever experienced on Earth. There are dense clusters where stars live only a light year apart. In certain regions of the Milky Way, stars form in such great numbers that they end up packed remarkably close together. Within these dense clusters, neighboring stars may be separated by only a single light year, far closer than the distance between the Sunday and its nearest stellar neighbor. The strong gravitational pull inside these clusters shapes the motion of every star within them. Their combined light creates dazzling scenes that would fill the sky for any planet orbiting there. Over time, gravitational interactions slowly push some stars outward, causing the cluster to lose members. Yet the densest clusters can remain tightly bound for very long periods. Studying them offers insight into the earliest stages of stellar evolution and the crowded environments where many stars are born. These compact clusters show that the Milky Way contains regions of deep solitude, as well as places of extraordinary crowding, revealing vibrant stellar communities at the beginning of their lives. The galactic center contains arcs of energized gas that twist like ribbons. Near the heart of the Milky Way, clouds of gas are energized by intense radiation and powerful magnetic fields surrounding the central black hole. These forces stretch and shape the gas into long, elegant arcs that curve and twist through the darkness. The structures glow in radio and infrared light, revealing their fine details. Many of these arcs trace the paths of magnetic fields, threading the region, while others form where energetic particles collide with gas, producing bright filaments. Observing these ribbon-like structures helps astronomers map the complex interactions at the galaxy's core. They show how gas moves, how magnetic energy is distributed, and how past events have shaped the environment. Though their appearance is graceful, they are forged by extreme and dynamic forces. Their flowing forms add unexpected beauty to one of the most intense regions of the Milky Way, where gravity and energy continually sculpt space. Some worlds orbit stars that erupt with intense flares of radiation. Throughout the Milky Way, certain stars release sudden bursts of energy that surge outward like powerful shocks. These flares occur when magnetic fields on the star rapidly rearrange, releasing heat and light far stronger than the star's normal output. Planets orbiting close to such stars are exposed to sharp waves of radiation that can heat their atmospheres, alter their chemistry, or slowly strip away their upper layers. Yet some planets endure these harsh conditions, developing atmospheres that adapt over time. Observing these systems helps astronomers understand how stellar flares shape planetary environments and influence the potential for habitability. The strength of these flares varies, with some stars erupting only occasionally and others flaring frequently. On these worlds, skies can brighten suddenly, repeatedly transforming atmospheric conditions. The idea of planets circling such volatile suns adds a dramatic sense of diversity to the galaxy, showing that stability and habitability are shaped by far more than steady sunlight alone. The Milky Way also contains enigmatic sources of gamma-ray bursts. Scattered throughout the galaxy are rare objects capable of releasing brief flashes of gamma radiation, the most energetic form of light known. These bursts are sudden, short-lived, and extraordinarily powerful. Some occur when dense stellar remnants collide, while others may be driven by extreme magnetic processes within compact stars. Because gamma-ray bursts appear and fade so quickly, they are difficult to observe, requiring instruments to be pointed in exactly the right direction at the right moment. When detected, they offer valuable insight into the most extreme physics in the universe. The energy released in a single burst can exceed the combined output of many stars, revealing just how violent and energetic certain processes within the Milky Way can be. Yet each event may last only seconds. These powerful flashes briefly illuminate the regions around their sources, revealing conditions that cannot be recreated anywhere else. Studying them allows astronomers to probe the nature of extreme magnetic fields, gravity, and ultra-dense matter. Although such bursts are rare, their existence shows that the Milky Way hosts events of astonishing intensity. They offer fleeting glimpses into the most powerful processes shaping the lives of compact stars. There are regions where stars form in chains, like beads on a string. In some parts of the Milky Way, stars do not emerge in clusters or scattered groups, but instead appear along long, narrow lines. These bead-like formations arise when gas within a molecular cloud becomes compressed along a single filament. As the filament contracts, it fragments into regularly spaced dense pockets, that collapse into stars. The result is a chain of newborn suns tracing the shape of the original gas structure. Observing these stellar chains reveals how gravity, turbulence, and magnetic fields work together during star formation. The even spacing of the stars provides clues about the physical conditions inside the filament before it broke apart. Over time, these regions change as young stars ignite, and their radiation reshapes the surrounding gas. Chains of stars help astronomers understand how large-scale structures in the galaxy influence smaller-scale processes. They show that even simple strands of gas can give rise to orderly and elegant patterns of starlight, adding delicate beauty to the Milky Way's star-forming regions. The galaxy also contains enormous clouds that block entire patches of starlight. The Milky Way holds giant concentrations of dust and gas so dense that they obscure all the stars behind them. These dark nebulae appear as empty voids against the glowing background of the galaxy, yet they are filled with material. Dust grains within them absorb and scatter visible light, hiding vast regions from view. Inside these clouds, temperatures drop to extremely low levels, allowing molecules to form in sheltered conditions. Over time, gravity can cause parts of the cloud to collapse, giving rise to new stars. Although they appear dark and empty, these regions are among the most active and important parts of the galaxy. Infrared and radio observations reveal the hidden structures within them, showing dense knots of gas where future stars will ignite. These massive clouds shape the Milky Way's appearance, carving dark lanes through its bright band of starlight. Their quiet presence reminds us that what looks like emptiness often contains the seeds of creation. Some red dwarfs burn so slowly that they may outlive the universe as we know it. Red dwarfs are the smallest and coolest stars capable of sustaining nuclear fusion. Their low mass makes them remarkably efficient at using their hydrogen fuel. As a result, they burn at a slow, steady rate and can shine for trillions of years, far longer than the current age of the universe. Many red dwarfs forming today will still be glowing long after larger stars have faded into remnants. Their gentle light and long-term stability make them common hosts for planets. Because they endure for such immense spans of time, any worlds orbiting them have extraordinary opportunities to evolve. Studying red dwarfs helps astronomers understand stellar lifetimes and the far future of the galaxy. These stars are quiet, persistent sources of light that dominate the Milky Way's population. Their longevity offers a sense of cosmic continuity and hints at what the galaxy may look like in distant epochs, when only the longest-lived stars remain. The Milky Way hides star factories buried deep within dark dust. Within the densest clouds of dust and gas lie star-forming regions completely invisible to ordinary telescopes. These hidden nurseries are so thoroughly shrouded that even the light from newborn stars cannot escape at visible wavelengths. Infrared observations reveal their presence, uncovering clusters of young stars, still in the earliest stages of formation. Inside these dark regions, cold gas collapses under gravity, assembling new stars piece by piece. The surrounding dust plays a crucial role by shielding the forming stars from harsh radiation. As the stars grow stronger, their winds and radiation slowly carve openings in the dust, allowing their light to emerge. These concealed nurseries are among the most active sites in the galaxy, producing new generations of stars that will eventually populate the spiral arms. They remind us that much of the Milky Way's activity unfolds behind thick veils of dust, far from direct view. Some stars are hurled to extreme speeds when their companions explode. When a star in a binary system explodes as a supernova, the sudden release of energy can shatter the fragile balance that once bound the pair together. If the surviving star is caught at the right moment, it can be hurled outward at extraordinary speed. These runaway stars travel far faster than most stars in the Milky Way, their rapid motion marking the violence of the event that set them free. As they move through the galaxy, they carry chemical signatures from their place of origin, preserving clues about their past. Studying these fast-moving stars helps astronomers understand the outcomes of stellar explosions and the dynamics of binary systems. Their extreme velocities also reveal details about the galaxy's gravitational structure. These swift travelers remind us that the calm appearance of the night sky conceals records of powerful and dramatic events. The galaxy also contains solar systems with planets that follow wildly tilted orbits. Not all planets circle their stars in neat, flat planes. Some move along steeply angled paths, orbiting at sharp tilts compared to their neighboring worlds. These unusual orbits can result from past encounters with other planets, close passes by nearby stars, or the gravitational influence of distant companions. Such extreme angles can strongly affect a planet's climate and long-term stability. Seasons may become intense, and patterns of daylight can vary dramatically over time. Observing these systems helps astronomers understand the chaotic processes that shape planetary systems. The existence of tilted orbits shows that solar systems can evolve in unexpected ways, forming arrangements very different from the orderly structure of our own. These worlds highlight the remarkable diversity of planetary motion throughout the Milky Way. Some worlds are covered in ice that never melts. In the outer reaches of the galaxy, or around stars that emit very little heat, certain planets remain frozen from their surfaces down to their cores. Thick, icy crusts can extend for kilometers, sealing away oceans or rocky interiors beneath solid layers. These planets may have atmospheres too thin to retain warmth, or they may orbit stars so cool that temperatures never rise above freezing. Others exist as rogue planets, drifting through darkness, where internal heat slowly fades until the surface becomes entirely frozen. Though these worlds appear still and silent, their interiors may remain active if enough heat lingers from their formation. Studying frozen planets helps astronomers understand how worlds cool over time and how different environments evolve. Their quiet, unchanging surfaces stand in stark contrast to the dynamic weather and geology of warmer planets. These icy realms show that the Milky Way contains environments where cold reigns completely. The Milky Way also holds electrically charged nebulae that glow with a ghostly light. Certain nebulae emit faint, eerie illumination created by charged particles moving through magnetic fields. These ionized regions form when energetic radiation strips electrons from atoms, turning gas into plasma. As electrons recombine with ions or spiral along magnetic structures, they release soft, otherworldly light detectable across various wavelengths. Such nebulae often appear near hot stars or in regions shaped by ancient explosions. Their glow reveals the presence of powerful forces acting on the gas. Observing these regions allows astronomers to trace magnetic fields that would otherwise remain invisible. The light they emit carries information about temperature, density, and the processes energizing the gas. These nebulae add an ethereal beauty to the Milky Way, showing how even faint light can tell rich stories about the flow of energy through space. There are also stars that form in triple systems. In some parts of the Milky Way, stars are born not alone or in pairs, but in groups of three bound together by gravity. These triple systems arise within dense clouds, where several fragments collapse at nearly the same time. Depending on their masses and separations, the stars can arrange themselves into stable configurations. Often, two stars orbit closely while the third travels farther out. In other cases, all three follow elongated paths that weave around a shared center of gravity. These complex motions can remain stable for millions or even billions of years. Studying triple systems helps astronomers understand how stars influence one another from their earliest stages. Their interactions can shape the formation of planets, altering their orbits or preventing them from forming at all. Some triple systems eventually become unstable as the stars evolve, breaking apart and sending one member drifting away into the galaxy. Others remain bound together for their entire lifetimes. These enduring systems reveal the complex and varied environments in which stars are born, showing that gravity often creates arrangements far more intricate than solitary suns. Some worlds orbit their stars on paths so eccentric that they freeze and boil within a single year. Across the Milky Way, there are planets that follow extremely elongated orbits. Rather than moving along gentle, nearly circular paths, they travel on stretched ellipses that carry them from distant, frigid regions to blisteringly close passes around their stars. When these planets drift far away, their atmospheres can freeze, forming layers of frost or dense clouds of ice crystals. As they swing back inward, temperatures rise rapidly. Ice melts, gases expand, and entire atmospheres can transform within weeks. These dramatic cycles create environments unlike anything found on Earth. The surfaces and skies of such worlds are constantly reshaped by alternating extremes of boiling heat and deep cold. Highly eccentric orbits often arise from close encounters with other planets or the gravitational pull of distant companions. Studying these chaotic paths helps astronomers understand how planetary systems evolve after violent interactions. These extreme worlds demonstrate how profoundly orbital shape can influence climate and potential habitability. The galaxy also contains clouds heated by invisible radiation from distant events. Throughout the Milky Way are gas clouds warmed by radiation whose sources lie far away, making the heating seem almost mysterious. These clouds are not always near young stars or recent supernovas, yet they glow with temperatures higher than expected. Their warmth comes from high-energy photons that travel vast distances through space. Such radiation may originate from ancient explosions, energetic regions near the galactic center, or compact objects that emit powerful light. When these photons strike gas clouds, they transfer energy and raise the temperature of the material. Observing these warmed regions allows astronomers to map how radiation flows through the galaxy, revealing how past events continue to affect areas far removed from their origins. These gently heated clouds act as subtle traces of energy moving silently through space, showing that even seemingly quiet regions are shaped by ongoing interactions between light and matter. Some planets are sculpted into distorted shapes by tidal forces. When a planet orbits very close to its star or exists alongside a massive companion, uneven gravitational pull can stretch it away from a perfect sphere. The side facing the star feels a stronger attraction, while the far side experiences less. Over time, this imbalance can elongate the planet, giving it a shape resembling an egg or a tear. Such distortion affects the planet's interior, generating heat through friction as material flexes and shifts. This added warmth can drive volcanic activity or alter atmospheric circulation. In some cases, planets orbit so closely that one side remains permanently heated, while their stretched shapes intensify temperature differences. Observing these distorted worlds helps astronomers understand how gravity sculpts planetary bodies. They show that planets are not always round, and that strong gravitational interactions can reshape entire worlds into unusual forms. The Milky Way also holds regions filled with primordial hydrogen. Scattered throughout the galaxy are pockets of hydrogen that have remained largely unchanged since the earliest eras of the universe. This gas existed before many generations of stars were born. While much of the Milky Way's hydrogen has been processed through stars and enriched with heavier elements, these primordial regions preserve a simpler chemical state. Their presence helps astronomers trace the galaxy's early history and understand how it grew from smaller structures. These clouds are cold, faint, and difficult to detect, yet they play a crucial role by supplying material to star-forming regions. They also allow scientists to compare present-day galactic environments with those of the distant past. Primordial hydrogen stands as a quiet reminder of the universe's beginnings, still drifting through the arms and halo of the Milky Way. There are stars that collapse into dense remnants without exploding, Not every massive star ends its life in a brilliant supernova. Some undergo a direct collapse, forming a dense remnant with little outward display. In these cases, the star's internal structure fails so rapidly that its core becomes a black hole or neutron star without a dramatic explosion. This silent ending leaves few visible traces. Yet it marks one of the most extreme transformations a star can experience. In these cases, the outer layers fall inward rather than being hurled into space. Such silent endings are difficult to detect because they produce few obvious signals. Astronomers search for stars that simply fade away without explanation, or for subtle gravitational effects that hint a compact remnant has formed. These quiet collapses help scientists understand the fine thresholds that separate explosive deaths from silent ones. They reveal a more complex picture of stellar endings, where the final fate of a star depends on delicate balances of mass, rotation, and internal structure. Some worlds are born in chaotic systems of multiple stars. In the Milky Way, certain planetary systems form within groups of 3 or more stars. These environments are dominated by shifting gravitational forces that constantly influence the paths of growing planets. Disks of dust and gas twist and wobble, shaping worlds that must find stable orbits amid competing pulls. Some planets end up circling a single star within the group. Others settle into orbits around pairs of stars. In rare cases, planets loop around all the stars together in wide, shared paths. The inherent chaos of these systems leads to many outcomes. Some planets are ejected and become rogues, while others survive in carefully balanced orbits that remain stable for long periods. Studying these complex arrangements helps astronomers understand how planets can form under extreme conditions. They show that planetary birth is possible even in environments filled with disorder and constant change. The galactic center contains whirling disks of hot dust. Near the Milky Way's core, spiraling disks of dust surround the central black hole. These disks shine brightly in infrared light as dust grains absorb intense radiation and heat to extreme temperatures. The material moves along rapid spiral paths, shaped by gravity and magnetic forces. As the dust orbits, it interacts with surrounding gas, creating structures that shift and evolve over time. Observing these disks allows astronomers to study how material flows toward the black hole and how energy from the core influences the surrounding region. These glowing spirals reveal the restless nature of the galactic center, showing that even fine dust behaves dramatically under such powerful conditions, forming elegant shapes within the deep gravitational well. There are star-forming filaments that stretch like cosmic threads. In the Milky Way, some of the most active regions of starbirth appear as long, narrow filaments. These structures can extend for many light years and are filled with cold gas on the verge of collapse. Gravity slowly draws material inward along the filament, creating dense nodes where stars begin to form. The filament acts as a channel, feeding gas into these growing cores. Observing these cosmic threads helps astronomers understand how large-scale structures within molecular clouds guide star formation. They show that the birth of stars is often organized following the flow of material along elongated pathways. These filaments bring a sense of order to the apparent chaos of interstellar clouds, shaping where new generations of stars ignite. Some stars live their entire lives in near-perfect isolation. While many stars form in clusters or associations, others drift so far from their neighbors that they spend billions of years almost completely alone. These isolated stars rarely experience close encounters or strong external influences. Their environments remain calm, largely free from nearby radiation or disruptive gravitational forces. Studying such stars offers insight into how stellar evolution unfolds without outside interference. Any planets they host may enjoy unusually stable conditions. These quiet stars move gently through the galaxy on wide, unhurried orbits, that keep them far from crowded regions. Their solitude reveals the wide range of environments within the Milky Way, reminding us that not all stars share their journeys with companions. Some shine alone from birth to death, carrying their solitary light across immense spans of time. The Milky Way also preserves ancient stellar fossils, locked in their original chemistry. Scattered across the galaxy are stars so old that they retain the chemical signatures of the early universe. These stellar relics formed before the Milky Way became enriched with heavy elements. Their atmospheres contain little beyond hydrogen and helium, with only trace amounts of elements created shortly after the universe began. Because they have remained largely unchanged for billions of years, these stars provide a direct window into the distant past. Their faint light carries information about the primordial conditions from which the first generations of stars emerged. Many of these ancient stars reside in the galactic halo, where low densities of gas and radiation have allowed them to remain largely undisturbed. Their stable structures and simple chemical makeup enable astronomers to study the earliest patterns of star formation. These stellar relics show how the Milky Way grew from modest beginnings into the spiral galaxy we see today. They remind us that even now, untouched fragments of cosmic history drift quietly through the galaxy, glowing with the preserved chemistry of the first generations of starlight. Some worlds orbit stars that are barely stable. In certain systems within the Milky Way, planets revolve around stars that exist on the edge of instability. These stars may be rapidly consuming their fuel, beginning to expand into early giant phases, or oscillating between different brightness states. Their internal layers shift and pulse, creating turbulent conditions that can strongly affect nearby planets. Some release sudden bursts of energy that change the temperature and chemistry of surrounding space. Others undergo slow swelling or contraction that alters their luminosity over long periods. Planets orbiting such stars experience environments far more variable than Earth's, with climates that can shift dramatically as stellar output changes. Studying these systems helps astronomers understand how planets respond to unpredictable radiation sources and reveals the delicate balance required for a star to remain stable. These restless suns add complexity to the Milky Way's stellar population, showing that not all stars provide calm, predictable light. There are regions where gravity sculpts clouds into towering pillars. In many star-forming areas of the Milky Way, enormous clouds of gas and dust are carved into dramatic column-like shapes. These pillars form when intense radiation and stellar winds from nearby massive stars erode the surrounding material. Denser portions of the cloud resist this erosion and remain standing as elongated structures. Within these pillars, gravity draws material inward, allowing new stars to form at their tips or deep within their protected cores. Over time, the pillars can stretch, twist, or fragment as radiation continues to shape them. Observing these formations helps astronomers understand how powerful forces guide star birth. Their striking shapes reveal where young stars are actively influencing their surroundings and where future generations are about to emerge. These sculpted structures highlight the delicate balance between creation and destruction in the galaxy, standing as intricate carvings of gas and dust shaped by light, gravity, and turbulent stellar energy. The galaxy also contains stars with exotic elemental atmospheres. Some stars in the Milky Way display chemical compositions very different from those of typical stars. Instead of being dominated by hydrogen and helium, their atmospheres show strong signatures of rare elements such as carbon, zirconium, strontium, or even heavier atoms formed through unusual nuclear processes. Some of these stars originated from material enriched by ancient collisions between compact objects. Others developed unusual compositions through internal mixing or by drawing material from a companion star. Their distinctive spectra reveal details about extreme stages of stellar evolution and the rare conditions that create such elements. Studying these stars allows astronomers to trace how heavy elements are produced and spread throughout the galaxy. Their chemical fingerprints serve as clues to events that occurred long before the Sunday formed. These stars illustrate the remarkable diversity of stellar compositions in the Milky Way. Their exotic atmospheres, glowing with the products of rare cosmic processes. Some planetary ring systems stretch wider than Earth's orbit. Within the Milky Way are planets whose rings far exceed anything seen in our own solar system. These vast ring systems can extend farther than the distance between Earth and the Sunday. Composed of dust, ice, and rocky fragments, they span enormous regions of space. Such massive rings often form around young planets, still collecting material, or around worlds that have captured debris from nearby objects. Their structure is shaped by the planet's gravity, the motions of small moons, and the influence of stellar radiation. Observing these immense rings helps astronomers understand the processes that sculpt planetary systems during their earlier stages. The immense scale of these rings suggests that many worlds pass through dramatic periods of collision and fragmentation. These enormous structures shimmer faintly in starlight, forming wide, delicate halos that sweep around their host planets. They demonstrate the astonishing range of scale found among planetary systems, far exceeding the familiar rings of Saturn. The Milky Way also holds stellar remnants that drift slowly through the darkness. After stars exhaust their fuel, some collapse into compact remnants that emit only faint light. These include white dwarfs, neutron stars, and black holes moving quietly through the galaxy. Many wander alone, far from the regions where they were born. Their slow journeys carry them through areas of varying density and temperature. Some pass through clouds of gas, collecting thin layers of material that produce subtle emissions. Others remain nearly invisible, detectable only through their gravitational influence on nearby objects. Studying these remnants reveals the long-term evolution of stars and the fate of stellar material. Their presence reminds us that the galaxy is filled not only with bright, youthful stars, but also with ancient survivors from earlier generations. These drifting remnants embody the final stages of stellar life, moving gently through the dark, long after their parent stars have faded. Some solar systems form with multiple giant planets packed closely together. In certain regions of the Milky Way, young stars give rise to systems containing several massive planets crowded into tight orbits. These giants may begin as large clumps of gas and dust spread across a disk, growing rapidly as they gather material. When many such planets form at once, their gravitational interactions create a highly dynamic environment. They can push one another into new paths, exchange positions, or even eject one another into deep space. Some systems eventually settle into stable arrangements, while others remain chaotic for millions of years. Studying these crowded systems helps astronomers understand how planetary architectures emerge from complex beginnings. The presence of multiple giants in close quarters shows how flexible and varied planetary formation can be. These bustling systems reveal that not all solar systems develop with orderly spacing. Some begin as crowded neighborhoods shaped by constant motion and gravitational negotiation. The galaxy also contains high-energy arcs, created by magnetic whiplash. In certain regions of the Milky Way, magnetic fields twist and strain under intense pressure. When they suddenly snap and realign, the released energy forms sweeping arcs of glowing gas. These features arise when tangled magnetic lines rapidly reorganize, accelerating charged particles that emit light in radio or X-ray wavelengths. Such high-energy arcs may appear near young stars, supernova remnants, or dense regions where magnetic fields are especially strong. Observing them helps astronomers understand how magnetic energy shapes the interstellar medium. These arcs reveal hidden forces that influence gas clouds, radiation, and cosmic rays. Their presence adds a sense of motion and vitality to the Milky Way, showing that even invisible magnetic structures can produce dramatic and beautiful effects. Some stars shed jets that stretch across space for many light years, Certain stars generate narrow streams of material that extend far into their surroundings. These jets form when gas spirals onto a star through a rotating disk, while magnetic fields channel part of that material into thin, fast-moving beams launched at high speeds. In some cases, the jets grow to lengths of many light-years, carving channels through nearby clouds. Where they collide with gas, they glow brightly, forming knots and arcs of light that slowly drift and change. Observing these structures helps astronomers understand how stars grow and how energy moves through star-forming regions. The jets reveal the powerful roles of magnetism and rotation during the early stages of stellar development. Their immense reach shows how even young stars can profoundly shape their surroundings. The Milky Way also holds worlds that form in darkness, far from any starlight. Not all planets are born near bright stars. Some take shape in the outer regions of young systems, where sunlight is weak or nearly absent. In these distant zones, gas and dust can gather into planets that receive little radiation. Their surfaces remain cold, and their atmospheres develop under dim conditions. Some of these worlds may later drift inward toward warmer regions, while others remain forever in darkness, orbiting far from any source of heat. The environments in which they form differ greatly from those near stars. Studying these distant planets helps astronomers understand the full range of planetary birthplaces. These shadowed worlds show that planet formation is not limited to bright, active regions. Even the cold outer edges of disks can produce fully formed planets that move in deep quiet, far from the warmth of starlight. Thank you for spending this quiet time beneath the Milky Way tonight. Let the thought of that vast river of starlight rest gently with you, not as something to analyze or follow, but as a calm presence far above the night. The galaxy can remain in the background, now silent and steady, like a soft glow behind closed eyes. If these gentle journeys bring you peace, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. As you settle into the quiet, imagine the slow drift of stars overhead. Picture the hush between them, the deep stillness filling the spaces where light takes its time to travel. Let that stillness rise around you. Let it soften your breathing and loosen the last tight places in your mind. You do not need to reach for sleep. It will arrive naturally, like darkness spreading across the sky. And if you are still awake, another gentle journey will be waiting whenever you are ready. If your eyes are growing heavy, you can let them close and drift softly into rest. Good night.